All right, let's continue. Now let's embark on an exploration of the subject, the why and what of observability in 2023 with Ben Evans. Ben is a distinguished figure in the field of observability, serving as the observability lead and senior principal software engineer at Red Hat Runtimes. His career includes leadership roles as the lead architect for Instrumentation at New Relic and co-founding jClarity, a performance tools startup, eventually acquired by Microsoft. Moreover, he has continued his experience as the chief architect for listed derivatives at Deutsche Bank and as a senior technical instructor for Morgan Stanley. Ben's commitment to the Java community is underscored by his status as a Java champion and his immersive 6-year tenure on the Java Community Process Executive Committee, where he played a pivotal role in shaping new standards for the Java platform. Beyond his advocacy for the Java ecosystem, Ben is an accomplished author with 7 published books, including notable titles like The Well-Grounded Java Developer, Optimizing Java, and the latest editions of Java in a Nutshell. His technical articles consistently engage thousands of developers each month, making him a respected voice in the developer community. Furthermore, Ben's expertise extends to the global stage as he frequently shares his insights as a speaker and educator. He covers a wide range of topics, including the Java platform, observability, systems architecture, performance optimization, and concurrency, captivating audiences at various companies and conferences worldwide. We are honored to have him here with us today and shed light on the fascinating world of observability this year. Welcome to the stage, Ben.
Thank you for that lovely introduction, Ekaterina. You've, I think, just negated the need for me to do my first couple of slides where I introduce myself, as you've already done it. So I shall skip straight on to say thank you, of course, to all of our sponsors, particularly as 2 of my publishers are up there on that list. So that's always nice to see. We talked about this, we talked about this. So let's move on to taking the temperature. I always like to do this in my talks, and there's just about enough light for me to see everybody. So hands up if you are using, let's say, Prometheus as an observability technology. Okay, about 1/3 of the room. That's a bit less than I was expecting, but decent numbers. OpenTelemetry. Who's got OpenTelemetry switched on? Again, about the same. That's interesting, because each time I give a variation or an update of this talk, I keep asking for those numbers, and the OTel numbers keep climbing. And that's a topic I shall come back to later in the talk, but that's interesting. A Java-specific one this time, Micrometer. If anyone's got Micrometer in stack. Oh, wow, lots of Micrometer fans. That's cool. And what about Elk? Who's got an Elk stack for logging? Oh, okay, that's actually pretty much the same numbers as Prometheus, and in fact, quite a lot of the same hands. So that is perhaps not that surprising. Okay. Now, the other question is, how mature would you say your deployment is? Are you fully deployed and using it in production every day? Hands up. Okay, that's interesting. That's about 1/3 of the room, but some of the hands that went up there weren't hands that went up for any of the previous questions. So that's kind of interesting. I'd love to hear what the observability texts that you're using actually are in that case, so maybe come and find me after the talk. Okay, so fully deployed, rolling out. Who's still rolling out their observability deployment? Yeah, there's still quite a few hands. And what about planning? Who's got one in the planning stages but not actually there yet? A few hands. And haven't started yet, don't have any kind of observability tech. Okay, well that is a very encouraging to see how few hands went up for none. When I gave a version of this talk about a year ago, we were seeing substantial numbers of people who still weren't doing any kind of observability at all. So that's encouraging. Okay, thank you for giving me some more data points. I always do appreciate them. So let's move on to the real content of the talk. We're going to talk about what observability is and specifically how we need it to understand cloud-native applications. And as we'll talk about, there are some subtleties and some complexities in there which make it essentially a necessity for cloud-native. We'll talk about the types of data we need to collect, and of course, because this is GSAS, we will also talk about the architectural implications that there are. Okay? So, observability sometimes gets a bit of a bad rep, in my opinion. People seem to think that it's very complicated and perhaps nebulous and not easy to pin down, and it's really not. You can actually frame it in really kind of concrete and simple terms. You need to do 4 things. You need to instrument your systems and your applications to collect observability data. And all right, I'm kind of fudging it a little bit here because I haven't told you what observability data is, but we won't worry about that right now. And then we have to send it to a system that can store and analyze it. And the purpose of that, of course, is not because we then have a nice, pretty system all full of lovely observability data, which we then completely ignore. I have actually seen people who do that. I've no idea why, but they do. So we want to get insights for DevOps, for management, and SREs, of course, into our systems. And critically, and this is, I think, one of the points about observability which is non-obvious, and I think it was probably charity majors who first came up with this idea. For an observability system to be useful, it's kind of like a scientific tool. You have to be able to get answers to questions that you didn't know you had when you started working with it. Because this is, in some sense, more like experimental or empirical science rather than traditional software development. And so the sets of skills you need are somewhat different. Also, hiding in here is our first and most important, yes, quite possibly our most important architectural point of all. It's the second line down. Send this data to a system that can store and analyze it. Now, I always feel embarrassed when I have to tell a room full of people this, but I keep seeing systems where they don't know or haven't thought about this, so I keep having to tell people. The system that you send the observability data into must be separate from your production system. Why? Well, because when your production system is broken, you need the observability data to analyze it. And how are you going to get to the observability data which is stored in your production system to fix the production system when the production system is broken? Right? Fairly basic point. You need to exfiltrate that data and put it somewhere else. This comes back to the closing remarks, I think, in one of the last questions we had in the last talk, which was about the architectural assumptions from an observability system are that it must be simple, it must be robust, it must be conservative, and most of all, it must not be upgraded as part of the same turnover that upgrades production. Why? Because if you do your observability system and your production on the same turnover, you run the risk of breaking both simultaneously, and you don't want that. Okay? So already you can see that there are some pieces of architecture which come out of observability really naturally, even with just the definitions we have. There are more formal versions of this, of course. There's systems control theory, where you can talk about the internal state of the system, and that also speaks to the notion of this of empirical science. And finally, the answers that you get from your system must be actionable. You must actually be able to tell something about the system from it and be able to make corrections. So here's an example. This is a real-life actionable insight, which I was able to drag out of a system, about 18 months ago. And, oh yeah, as I'm here, I might as well mention this. If any of you are running Java or JVM applications, you have to run them in containers which have more than one core. The same, by the way, is also true of Go applications. If they're running in single-core containers, you're getting performance behavior that you almost certainly don't expect, because it selects a different garbage collector, among other things. So this is the type of insight that you should be able to get out of your observability system once it's installed and is running correctly. Okay? So that's the basic, very high-level view of what we're going to do. It's worth thinking a little bit about where observability comes from and why it relates specifically to cloud native. Now, application performance monitoring, which is one of the threads, one of the strands which lead us into observability, it's not the only one. You can think about operational practice and large-scale automation as also being some of the drivers which lead us to observability. But APM is definitely a major one. And this is, I think, quite a 15-year history. That's quite a long time in software architecture and software development terms. And, of course, the world was very different back then. We had a release cycle that we used to measure in months. Right? So you would have a system which was stable between releases, and releases would happen every 3 months, in some cases every 6 months. Our systems were overwhelmingly monoliths. There was some notion of service-based architecture at that point, and some of the better places. I was at Morgan Stanley at the time, and they very much believed in a very lightweight service-orientated architecture approach. And so in some ways, I kind of had a taste of the future back then. And of course, it was all on premises. You had servers with individual names. They lived in racks. You had to predict how many servers you were going to need in 3 months' time, so they could be ordered and delivered and physically assembled into your racks, which existed in a real place that you could go and visit. So just a reminder of how things have changed. The point that I really want to draw your attention to is the stability of the architecture between releases. That is actually just a slight spoiler for why cloud native is different, but only a slight spoiler. Because the architecture is stable between releases for months at a time, operations teams were able to develop an intuition for where they were likely to break. The places you needed to put instrumentation were relatively obvious and relatively simple architectures, and because they were stable, it was possible to just say, well, we've upgraded, we need to put a bit more monitoring in there or over there in the architecture. And of course, things used to look like this. Good old 3-tier web application. I sometimes miss these, and I sometimes think we don't reuse old patterns enough. There are plenty of places, plenty of domains where a 3-tier web application is still absolutely fine. We don't have to use completely new techniques and the latest and greatest of everything just because we can. That's a different rant, though. Okay, so back to the present day. How do we understand cloud native? What makes cloud native different? Fundamentally, it's the more sources of change and more rapid change. Yes, our architectures are bigger. They are more complex, and they have more services and more components. That is certainly true. But for me, it is the rate of change, the rapidity with which we turn over new releases and modify our systems that really does it. Because what that does is it eliminates that punctuated equilibrium where the architecture is stable. And that means that your ability to develop an intuition about it in that way is gone, because it's not stable. Tomorrow, in larger organizations, some team you've never heard of may turn on a service which suddenly starts hitting yours, and the load pattern that you thought you understood completely changes. I think there are probably some folks in the room who've had that experience once or twice, and it can be extremely painful. So it's that which is at the heart of why we need observability into our systems. Now, what else could we say? Well, there are also new technologies with new behaviors. There's things which dynamically scale. There's Kubernetes. Yay, Kubernetes. There's also things like function as a service and Kafka and all sorts of other things which have changed the way that we architect certain types of systems. Mostly, hopefully, for the better, but not always. So yes, we need to understand those things as well, but I think everything is more ancillary to the fact that we have these architectures which just change all the time now. A slide about Java and containers with a link on it, which might be interesting if you do have Java tech stacks. Just leave that up for a few seconds so people can snap the link if they want it. Yeah, okay, cool. And of course, because I work for Red Hat, I have to, by law, show you a slide with OpenShift on it. OpenShift is our enterprise deployments of Kubernetes, and it tends to be bigger systems and government departments and stuff that like it. It's a pretty solid version of Kubernetes, but if you're not doing things at a big scale, if you're a little startup, it might not be right for you. But my point really with this slide, joking aside, is to show you that this is still recognizably a services-based topology. I mean, these things are mostly microservices now. There's a few things which are being run as appliances. Like we've got some Kafka up there, we've got some Camel, it's all good. But these things still look like services. One other point is, of course, there's a bunch of different languages here. So yes, some of it's in Java, but by no means all of it. We've got some Node, we've got some other bits as well. So another feature of our architectures as compared to 15 years ago is that they are much more heterogeneous. You have much more different types of technology in the stack than you might have thought. But still, this still looks like services, really. Then, of course, there are things which just don't. This is much more like an IoT or a cloud-based example. And here, the services are kind of just gone, right? We've got serverless, we've got a function as a service, which is our main data ingest. And then we've got a bunch of things which hang off the back of it. And this no longer really looks like a microservices architecture. And observability, we need to be able to understand and get insight into these types of systems as well. Okay, so this is basically just a summary of the points. Large numbers of smaller services, multiple relevant personas, heterogeneous tech stacks, and scale out of service clusters. Some of the things that we would expect to see in the architectures for today. But despite all of this change and all of these things which we need, our overall user perspective has not really changed that much. We still need to know things like how healthy is the system at a high level? What are the root causes of our errors and defects? Do we have any performance bottlenecks? Where are they? Which of these things is actually impacting customer experience? This last question is, of course, much more complicated than it was 15 years ago, because so many more of our architectures are able to operate in a degraded state. When you built smallish web applications, they were kind of either up or down. There weren't these cases where some services had failed, yet the application as a whole was mostly still working for most users. So there's some subtlety and some nuance in that last question, but it still remains there. So when I first started with APM, the world kind of looked like this. The only ways to get observability solutions, or proto-observability solutions, was to approach a vendor, and everything was proprietary, and you were locked into all the pieces, the instrumentation, the data collection, the data processing, and the visualization all came from the same vendor, and you just went out and wrote them a check for an annual subscription, of course, and they provided you with all the bits you needed. This is one of the other things which has changed, and it ties into the rest of the story about what happened to make observability come about. Okay, but I did promise earlier on that I would explain. I'd glossed over the point. I said we collect observability data and we send it somewhere else. I never explained what the data actually is. And there's a model for observability which is sometimes called the 3 pillars. Hands up if you've heard of the 3 pillars of observability. Okay, very interesting. Only a couple of people. Okay, wow. I'm glad I put these slides in now. So the 3 pillars are metrics, logs, and traces, effectively. Okay, so how are they? Well, what's a metric? Well, a metric describes a particular process over a known time interval. Logs, well, we all know what logs are. They're just, but thought about properly, they're kind of a record of discrete events that happen in the system over time. Generally speaking, we want our logs to be immutable. They should be written once and then only ever read after that. And then finally, we have traces. Traces show what is happening inside a process or across an entire distributed system, and which code is failing or which piece of the system is responsible for performance bottlenecks. Okay? As you can see, these are quite different in terms of data, and we'll talk about the characteristics which make them different in a minute or two. So let's just do some slightly bigger definitions for the 3 types first. So metrics measure specific activity over a time interval. There's typically 4 parts to a metric: timestamp, name, the value that you're recording, and some dimensions. And dimensions are different values for some tag. So the most simple way to think about a dimension is a key-value pair. There's a key and it's got some value. But there's slightly more subtlety to it than that. First of all, the values should be low cardinality. Why? Well, because you can have multiple tags. And the multiple dimensions means that the true cardinality of the metric can very quickly explode. Those of you who've dealt with badly configured Prometheus systems may well know what I'm talking about. So you need to keep the possible values of each tag to a very small subset, a very small set of potential values. That's the first point. The second point is, and this really is what makes a dimension, they must allow for aggregation. You must be able to take something and make a sensible aggregate out of it. So for example, CPU metric, okay? It's quite easy. You have two possible values for the dimension, system and user time, okay? That's a really good dimension. Why? Well, because there's only two possible values for the tag, and you can aggregate them sensibly by adding them together to get the total CPU. So a sensible aggregation exists across the dimension, we say. Something like temperature, let's suppose we have a monitoring system monitoring the temperature in different rooms of our house. That is not a dimension. Why? Well, because what good is it to know the sum of the temperatures in the kitchen and the bathroom? The average temperature? Maybe, but that's looking really quite questionable. So instead, in terms of the design of these things, it's probably better to model it as separate metrics in that case. It should also be pointed out that not all metric systems support dimensions or treat them as key value pairs directly. That's something I'll come back to later on. One other final and really important point is that the volume of metrics data that you get is independent of the request traffic, because it's just measuring a certain number over a time interval. And that, of course, is understood to mean a fixed time interval. If you're taking metrics every second, you get one metric value every second, whether the system's completely idle or whether it's absolutely overloaded. So there is no relationship between the metric volume, the volume of metric data, even, and the request traffic. Okay, simple examples. We've talked about CPU. There's probably a whole host of other things you can think of here that go into this category. The architectural aspects. So when thinking about metrics and which metric system to use, there's a bunch of things you can think about. We've talked about dimensionality. The other alternative is what's called long names, where you have to treat the name of the metric as meaning something and then do the stemming and the cutting it up to see what it really actually represents. And that's kind of what Prometheus does. Two other aspects which are important architecturally are the aggregation discipline, which basically is what you do with the data. Do you convert it to a certain rate before you publish it? Or do you send everything to the server and let the server sort it out? There are different reasons why you might choose each of these architecturally. Generally speaking, most systems tend to prefer client-side, but not everything does. And finally, there's the actual, the mechanism of network traffic. How are you sending the data to your observability system? Are you pushing it out from your application process, or is something else coming in and scraping it out of your process for you? And again, there's different systems that do different things here. I think I'll skip the Java metric slide and talk about logs instead. So logs are, well, immutable records. Once you've created them, put them in a log file, they happen over time. But here's where it starts to get a little bit more interesting. If you think about it, there are really possibly two different sorts of log. There's an unstructured log, which is just some text and possibly a bit of data that you've dumped out into it, which has a severity level. Info, debug. I hope nobody logs in debug in production. That's generally a very, very bad sign. Critical, etc. And then the second type of log that can be produced is a structured form, probably JSON, but without a severity level. And then the question is, are these two things really the same? Are they really different data subtypes? Is one of them a true log, which is unstructured, and is the other one really better thought of as an event? That is still an ongoing debate. I think the consensus is more falling that these things are conceptually different, but need to be handled in a similar way. We'll talk about that later. And then, just some examples of logs, syslog, platform logs, as well as the obvious application logs as well. Case study, just because it will come up later in the talk. From Java, logs are really easy. Every Java developer is very used to logs. This facading pattern is very common, and it's just a logging API. And the configuration determines what you do with the log. So from a developer's point of view, You don't care. You just write a log statement out, and it gets taken care of somehow. Other languages don't have this sort of long-standing history and sophisticated way of handling logs that Java does, which has a knock-on effect, which we'll talk about a bit later. Oh, also, just because I keep having people get this one wrong, there are two types of logging, centralized and distributed. A distributed system does not mean you have distributed logging. Virtually all distributed systems have centralized logging. All of the logs get sent to one central point on the network to be handled. Okay? A distributed logging system means something different. It means that there is some other architectural constraint in the system which prevents you from being able to do centralized logging. You only do distributed logging if you absolutely have to, because it's a massive pain. But sometimes network bandwidth, security, or other constraints mean that you have to adopt distributed logging. If you can possibly get away without, then you basically definitely should. Okay, so two things we were quite familiar with. We already know about metrics, of course, and we already know about logs, of course. Tracing is, I think, a topic which fewer developers are fully on board with yet. Hands up if you have a tracing system running in production. Okay, so not too bad, about a quarter of the room. That's good. So for everybody else, let me sort of explain how it works, and then I'll explain why you should have it. For each invocation, we want to figure out exactly what got called. Which instance or pod did we hit? Which method was called? How did the request perform? What was the result of it? And of course, in a distributed system, it's not quite that easy because there are other subcalls that it might trigger. And we end up with this sort of tree structure. Let me show you what I mean. So here we have like the world's simplest service. You have a browser. It makes an HTTP call across to the service. There's a trace duration, which is the intrinsic time for how long it took that to run, and back comes your result. Okay? And you're thinking, why has Ben got a big red dot over here on the right of his slide? Surely his laser pointer doesn't actually create dots that big, and sure enough, it doesn't. You'll see in a second. So okay, now we have a service, and let's add a database. So now our situation looks more like this. The intrinsic trace duration is still the red line, but now we're making a call over to the database, which produces us this second span, as they're called. So now we have a slightly more interesting graph, which has a red dot and a blue dot, and they represent the parent-child relationship of the overall trace and the subspan, or just the span underneath. Now let's add in a couple more components. We've got some auth, we've got some storage, and now we're making 3 separate subcalls. So that's fine. We've got a root node, and then we've got the tree structure underneath that. And then finally, just for fun, let's suppose that instead of talking to the auth service to get a token to talk to the DB, that the DB is authorized by making a call to the auth service itself. So now we have 2 subcalls. We've got the one to the DB and the one to the storage, but there is still a call to the auth, and so we end up with a topologically different tree of spans. So what do these things look like? Well, in JSON format, they look a bit like this. And these headers, the trace ID, which tells you what overall trace it is, the span ID, which corresponds to this specific span, and then the parent span ID. You need those last 2 so that you can restitch the individual spans back together. Because remember, these are distributed systems. These components are running probably on different containers. So you need to have some way of collecting the data from each point in the system, each container that participated in this transaction, and sending everything back. Okay, so let's talk about the components that go into a distributed tracing system. Well, first of all, we need instrumentation of application and middleware. Why? Well, we need to carry around these 3 identifiers, the trace ID, the span ID, and the parent span. But as noted, these are distributed systems, largely HTTP-based. So this information has got to get from container to container. And the only way to really do that is either by modifying the application to manually add those headers, or do something like an interceptor or some other sort of pattern like that, which will enable you to automatically add the headers so that they just propagate. And this is, of course, a W3C standard. The standard is called Trace Context, and it's been around for I forget how many years now. I'm too confused by pandemic years to actually figure whether it's 5 or 6, but it's about that sort of time. We then, of course, need to propagate the context. We need to ingest and store the data somewhere else. And then we need to search, retrieval, and visualization. So where we are with tools, and for the folks who don't have distributed tracing switched on yet, this is sort of your best of breed right now. You have OpenTelemetry providing the instrumentation piece. The context propagation is OpenTelemetry/W3C. There's a component called the collector, which we'll talk about later. It's kind of a bit of a stupid name because it doesn't actually collect data. And then you have backends, so maybe Jaeger. I think Tempo's got a backend as well these days. And then you need some components to do the visualization and the search and retrieval over the top. I should check this. Who is running open tracing? Is anyone still running open tracing or Zipkin? No? Okay, a couple of people were still running Zipkin. Yeah, you might want to think seriously about getting off that sooner rather than later, because it's not looking like the world's healthiest project anymore. And open tracing, of course, is completely archived and no longer being developed and not being mitigated against CVEs anymore. So if anyone does have open tracing, moving off that should be a fairly critical priority for you. Now, of all of these pieces, the hard part is visualization, the last step. Typically, and Jaeger was kind of the market leader here for a while, what we use is a trace view, which just shows the different spans effectively in the tree format that we originally saw them as. This is often too low level. In a large production system, you can find yourself running into issues of trying to find where the slow trace actually is. We definitely need new visualizations. So if there are folks who are more on the front-end side and more interested in user experience and visualization, this is something where an interesting approach or an interesting startup could make a real difference. Especially because, I don't know about everyone else, but I'm very much of the opinion that our systems are only going to get more complex and more sophisticated over time. I don't see a return to the halcyon days of three-tier web apps anytime soon. Final point is about data sampling. This is quite important. Traces, one of the reasons I think why people sometimes don't want to install them or are shy of them is because they can generate a lot of data. One of the key things to think about is how you sample that data in order to get meaningful results out of it. And generally, the accepted best practice is for most systems which are not super critical, you want to take 1% of the success results and about 100% of anything which showed an error code of any kind. And hopefully that unless your systems throw errors a great deal, that should be a manageable amount of data for you. Okay, so now that we've introduced the three types of data, we can ask the question, what can we do with it? And it's worth noting that you can source certain observables, certain measurements in various ways. You could, for example, get the overall response time from log files or metrics, or you could infer it from traces. But just because you can do something, it doesn't mean you should. And for many of these metrics, they are best got by a particular golden source. So an overall response time, you probably should get that from a trace, for example. And so here are the aspects of the data which I think make each data type unique. This is really why I like the three pillars model of observability. Not every practitioner in the space does like it. Some people prefer to think about observability in a different way. I get where they're coming from, but to me, the three data types that are represented here are very different in character. And so it makes sense to keep them as separate concepts. I also think that the three pillars model is much easier to teach to people who are new to the area. Some of the more sophisticated ways of looking at observability are great, but they sort of need you to understand observability quite well before they really click and make sense. So I tend to take the view that we have the three pillars, and so we should use them. In the case of metrics, our usage is trending and graphing. That's always what we do with metrics. And the characteristic that they have, which none of the other data types have, is that they are aggregatable. You can take a metric and you can boil it down to something more coarse-grained. You need to be careful how you do that. In particular, if you do things like percentiles or histograms, it may not be possible to further aggregate that data in a consistent way. So you do need to do a bit of statistics if you're going to do anything more than just basic aggregation. But that's an entire talk in itself. Logs. Well, the great thing about logs is you can grep for things in them. And as ops teams have been doing for, since time immemorial, that's what you do. Their characteristic, which separates them from the others, is that they are discrete events. They happen at a single point in time, and I suppose in space as well. And then finally, traces. Their usage is normally to identify slow or failing subcomponents or systems. And their characteristic, which makes them different from everything else, is that they are request scoped. This means, by the way, to return to an earlier thought, that the amount of trace data you collect is directly proportional to the number of requests you receive. Even if you are sampling and only taking 1% of traces, that's still a linear relationship. And very occasionally, especially in systems which decide for whatever reason that they need to take more data than that, and I've seen people who insist that they have to see 100% of the traces, well, a sudden spike in request traffic means a sudden spike in trace traffic, and you can swamp your own network by trying to send traces into the system. So you need to be a little bit careful and think about some of those aspects. That's why I tend to always sample, unless I've got a very good reason not to. Okay, so what sort of actionable insights? Because the key thing about observability is to talk about actionable insights. What can we do as SREs or DevOps with the data that we can see? So we've got a bunch of different things you might want to try and figure out here. A service alert, a timeout, a problem in the infrastructure, configuration, and a memory leak. Right, so 5 fairly typical issues with production systems that we might encounter. And there's a kind of a standard signal for finding each of these. For a service alert, it's the metrics, because you hopefully have got a metric set to alert on a service. Timeout, it's tracing, and so on. Probably also time to just talk about a couple of anti-patterns really quickly. One of the things that I've seen people do is to abuse log correlations. So they're like, we don't need to build a tracing system. We can do it all from the logs. Right? I have seen this implemented 8 or 9 times at least. I have never once seen an implementation that was robust enough compared to a distributed tracing solution for real. If you find yourself doing it, it's a sign that you need to put tracing in. But the argument, the logic goes, hey, we put an ID in everything, and it flows all the way through the logs, and then we can stitch it all back together by just looking at the logs. This works fine until, and yes, I've seen all of these issues, the logging components are set up correctly. Right? Maybe different components have different log levels, and all of a sudden, you've got a system which is only logging error level. Oh dear, that component is now invisible to the trace. IDs which are not created the same way. Some systems have UUIDs, and some of them have just long numbers. Oh dear. The IDs do not contain PII. Hands up if you know what PII stands for. Personally identifiable information, the sort of thing you never ever want to put into your logs. In one particularly special case, I saw a system where the IDs were literally a bunch of JSON PII that was base 64 encoded. So all you needed to do was to get a piece of log, decode it, and you had an entire person's stuff. And I was like, don't want to do that. And then, of course, you need to have a system which can keep up with log flow. And various other problems as well. So all in all, log correlation is kind of this. Can you do it? Yeah. And it's going to sort of work for a while, right up to the point where you remember that hammers are made out of really hard steel, these things are made out of really soft steel, and it's actually going to destroy your wrench as well as only be marginally operational at hammering nails in. The other anti-pattern that I've seen a certain amount is to shoehorn things into metrics. The one place where I know that was particularly egregious for this, and I suppose I can say this publicly now, was Twitter. Twitter used to do this a lot. where they would use a metric system to try to shove data into it that just isn't a good fit. Metrics are counters of gauges, they're aggregates, but you can't really shoehorn things into them. In particular, people try to abuse histograms to carry data they're not really meant to, and that becomes a problem because histograms have buckets, and if you try to aggregate two things together which have got different bucket sizes, you end up with a broken histogram that is not actually accurate. The other thing which is also worth saying is that you don't have to collect everything that's absolutely just because you can. Not everything that you can collect actually matters. Especially, one place I saw this, I've been doing some work on the open telemetry standards, and the runtime-specific metrics. People went a little bit crazy and started to try to get everything they possibly could into the runtimes metrics piece, including things like things that are uselessly coarse-grained. A 5-minute moving average of CPU, right, is virtually useless to virtually everyone. Why? Well, because if your 5-minute average is running high enough to alert, Kubernetes has already killed your pod. Right? So by the time you notice it and to be able to have an actionable insight and do anything about it, your processor's already dead. So the key question that I kind of try to use when thinking about building metric systems is, what is this going to help me debug? By having this metric available, what am I going to be able to see? What am I going to be able to learn about the internal state of my system in an outage if we put it in? And if I can't think of a good enough reason, just don't put it in. Turns out you need it after an outage, just add it back. So, okay, architectural implications overall. We've talked about the biggest one, which is the data needs to go somewhere else. But then there are some choices that we can make. And they have different trade-offs and implications, both for your application and for the observability component itself. The most common choices are to aggregate on the host and send the aggregates to software as a service, send everything to SaaS, keep everything on cluster, and roll your own. Skip forward. So this is aggregate on host, and this basically shows an example which uses open telemetry to gateway and send data into various backends that we have. You can do things like keep it on cluster, which is possible. There's a nice technology called eBPF, which is a kernel-based technology, which I quite like, but the problem with it is it generates vast amounts of data. So it's not really practical to use at scale across an entire system. You have to kind of do it per Kubernetes cluster. And that then, of course, leads you to other implications of that choice, which is now it's hard to debug problems which span more than one cluster, or a cascading failure which starts in one place and then ripples across your architecture. So there is that trade-off. Then there's the ability to roll your own. Having worked at New Relic and seen a couple of the other big open source projects, this is basically the pipeline you end up building. You may want to do other things, but pretty much a lot of them are going to look like this. The problem with this is that unless it's absolutely critical or you have some regulatory requirement to do this, this is almost certainly more expensive than just buying a vendor solution. In many, many cases, it's going to work out cheaper just to get a third party to do this for you. Because, of course, observability is about production outages. It's about reducing downtime. It's about impact to customers, which means it's a first-class concern. So your observability team suddenly now requires, well, if it needs to be 24/7, we're talking about follow the sun. We're talking about a team of 5, and all of the things that go with that. So for all of those reasons, I tend very hard to say if you can avoid rolling your own architecture, you should. Okay, so let's talk about OpenTelemetry. So I'll talk about the origins, what it is, and some of the components that are here. Basically, the very short version of the history is APM started off with proprietary vendors. Lots of companies didn't like that, and big places like Google certainly didn't want to pay proprietary companies that sort of money. So what started were a bunch of open source projects. Some of the names up there, the things which end up in the Elk stack, for example. And a few years ago, while I was at New Relic, in fact, there was this sort of inflection point, there was this flip in the market where everything suddenly went from being proprietary to being at least partially open source. And it's driven by economic factors, as these things so often are. If you've been around and working on open source for as long as I have, you've seen this happen in multiple markets, multiple verticals, suddenly reach a point where market pressure, effectively, makes it more efficient to cooperate with your competitors on a component which is effectively commoditized than it is for each of you to continue developing multiple proprietary versions of it. That's what happened with this part of the observability stack. Over time, people didn't want to spend the money needed to maintain all of the instrumentation and all of the client-side components that are needed. And so the logical conclusion, collaborate on an open source project. And that leads us to OpenTelemetry. So again, I think people don't always understand what it is, so let me explain what it is and what it's not. It is a set of standards. It is a set of data formats and a set of libraries for client-side, i.e. application instrumentation. That's pretty much it. It is not a data ingest, despite the collector, come back to that point. It's not an observability backend. You use it for getting data out of your systems and putting it, well, that's up to you. But it's for data exfiltration. The good thing about this means that instead of having to have like an OpenTelemetry exfiltrator and an OpenTelemetry backend, you can decouple the two. And that means that as architects, you have the choice of how to deploy it. You can send it to a vendor. And if you don't like that vendor in 6 months' time, you're still using OpenTelemetry. So you can send it to a different vendor. You can do all kinds of things with it. It's extremely cross-platform. It's not Java-specific. My examples are largely in Java because, well, it's a nice language, and because the Java implementation of OpenTelemetry is very mature. The Go implementation is also really mature as well. .NET, Node, yeah, they're okay. But once we start getting into Python and PHP and things like that, there are still some significant gaps. Because the way that the project is structured as open source, each language community is responsible for developing its own implementation of the overriding standard. So the standards and the formats are language independent, but each language community develops an implementation of that, and they are of varying maturity. It does work with bare metal and VMs, but it is definitely a cloud-first technology. And here is a slightly confusing diagram. I got this from the OpenTelemetry website, and they seem to be really proud of it, and I'm not quite sure why, because I think it's a bit messy. But let me change that into some text, which might be a little clearer. So what are the three pieces? The API, this is basically used to instrument apps and libraries if you need to develop some custom instrumentation. The SDK is the part which you use to configure your setup and actually work with it. Long-term support, yeah. This is another funny one. I don't quite know where they get their definition of long-term support from, but I don't particularly think 3 years is very long-term. But nevertheless, that's what the components, once they reach 1.0, are supported from. The components, specification, implementation, and the collector. The specification is the cross-language piece. That's where the parts on the previous slide fit in. One of the hard parts is actually defining what the data means, what we refer to as the semantic conventions. And trying to do that, especially consistently across languages, is actually quite difficult. For most open source developers, though, where they want to spend their time is in this middle column, the instrumentation. They want to write libraries and reusable code, which makes every library and every application written in your language observable completely out of the box. Again, support here for this varies between languages, but you'll just have to find out for your own specific setup. And then finally, the collector, which actually is more like a switching station for converting data into different protocols. It does not actually persist data. So you could argue that this is just APM with new marketing terms. Well, kinda, but not really, because you don't have any vendor lock-in. There's open specification of the protocols, there are open client components, there is a standardized set of architecture patterns and quality open source components coming out. So now, if we revisit our observability loop, two pieces of this have been completely commoditized. The instrumentation piece and the data collection piece are now basically open source components, pretty much standard. And then for the rest of it, well, you take your pick. Do you want to process with a particular vendor? You want to build your own open source pipeline? You can do what you like. The current status, distributed tracing and metrics are both at 1.0. Open tracing is completely replaced and gone. The Jaeger client libraries are completely replaced and gone. OpenTelemetry is really the only game in town for tracers, which has a serious future. Metrics is at 1.0, both for application and runtime. There is still some ongoing work. There's still a little bit of annoying detail in that space of figuring out what the metrics mean. But we're basically there. And will OpenTelemetry metrics replace Prometheus? Well, maybe as a client protocol. Maybe. But there are components, for example, where you can use OpenTelemetry to push your data out of your application and into an OpenTelemetry collector, which then stands up a Prometheus endpoint. So a Prometheus backend can just come in and grab that, but you're still exfiltrating and getting your data out using nothing but OTel. The sticking point is actually logging. It's not expected to reach 1.0 until later in 2023. Part of this is down to the question of whether it has two subtypes, true logs and events. And again, this one is where the language implementations having different maturity really bites us. Java's basically ready to go. Python is still looking really quite messy. And one of the things is they don't release a 1.0 status within the working groups until a minimum number of languages have reached that specified level. So yeah, I think I spoke to most of this already. The collector is just a service that translates protocols, so you can effectively do this. The collector is actually a really well-architected piece of code because it is designed to take in all sorts of different things and be very configurable and very extensible. So the design goals for the collector were basically these 5 things, and it does really pretty well at them all, I think. There's a new protocol, which is the OpenTelemetry protocol, OTLP. It's basically just about a wire protocol, so encoding and transport, how it actually looks like on the network. It's a very key concern is performance, because it has to be very fast and transmit potentially a lot of data with low overhead. Standard implementation is protobuf over HTTP2, and if you're fortunate enough to have gRPC or something like that, it's very happy. You can do it with HTTP and JSON. I wouldn't. Aggregation, I've talked about a little bit before, so let me just skip ahead and just say, yeah, in Java's case, we also have the nice thing that we have automatic instrumentation available. So you don't have to manually write tracing stuff into your code. You can just deploy a Java agent, and you get automatic instrumentation all the way through. There are still some problems with configuring it, making sure it doesn't send too much data and stuff, but that is a very nice way to do it. Not all other languages have that, but it's one of the nice ones. Okay, so I think I've talked about tracing and metrics. So I think I'll basically just take 2 slides and wrap up. So observability is reaching more and more developers, and it's gathering steam rapidly, especially in OpenTelemetry. My friends at New Relic tell me that they have seen a 30x increase in the number of OTel collectors. Equally, in the 12 months since they switched on beta support for OpenTelemetry about 2 years ago, in the first 12 months, they saw it grow to be 1/3 of their data ingest, which is roughly 3 billion data points per minute, which is just from nothing in 12 months when it was still in beta. That's not a technology growth that you see very often. That's why I'm so interested in it. That's why I'm putting so much of my time into working with OpenTelemetry, just because I've so rarely seen a developer technology take off quite like this. Logs will be 1.0 in end of 2023. That will be a big milestone. And I didn't believe this when I first saw this number in the back end of 2021. I think it was Gartner who said, by the end of 2023, OTel will be 60% of all the observability traffic that's seen. I didn't believe it. Now, it looks much like it was way too conservative an estimate. Having said that, we still have some challenges. There's a large diversity of tools and technologies in use. Even just hitting the market leaders, there were still plenty of hands that went up for observability technologies that I didn't talk about. The other thing is, and this is really an architectural point, there are different architectural options, and there are different mixes of technologies. That means that there is a very large matrix of possible things that could be deployed on any given production system. OpenTelemetry is, I think, a good way to tame some of that chaos, but even when using it, there are still choices that you have to make, and it is still maturing. The long tail is also, I think, a problem here. I do still run into open tracing deployments fairly regularly, and they really shouldn't be any left anymore. But this is software, and things hang around for longer than we expect. The interesting thing will be to see also what happens with logs, because logs do have this rich vendor space. There's already well-established proprietary and open source logging technologies which really own a lot of the market space. So will OpenTelemetry logs break into that? Will it become a player? Will it own the exfiltration space somehow and then integrate with things like Splunk? Don't know. But that's a market dynamics question, and we'll just have to see how it plays out. So it's an exciting time, an interesting time. There's a short reading list there, if you're interested in any of the things that I've talked about. The streaming systems book is sometimes called the Fish book. It's the Google SRE book about how they built the original versions of some of this open source stuff. It's quite a good read. And just to finish, my two most recent books are here, and I'm very happy to say that for anyone who wants it, we have a download link. My employer, Red Hat, are sponsoring a free download of the Java in a Nutshell latest edition. And with that, I think I'm slightly over, so I'd better stop here. Thanks very much.
Thank you, Ben. Thank you, Ben. All right. Let me ask the most voted question. So what are your thoughts on using a solution like Datadog for comprehensive monitoring and observability instead of creating a complex in-house solution using a stack of different tools?
Okay, so the question was basically, what about things like Datadog? So companies like Datadog and Dynatrace and New Relic are all vendor solutions, right? They're all what I referred to as vendor SaaS in the talk. So these companies are all moving towards the open source client components model with private proprietary backend services. And that's fine. You can just decide, I'm going to pay those companies each month. And what's also been interesting is the way that that licensing and pricing model has evolved, because now they're all essentially consumption-based pricing. You pay for the amount of data you send in, and you maybe pay for the number of developer seats you have. So that means that you can, to some extent, control your bill in a better way, rather than having to buy, old-school recurring software licenses. Lots of companies like them. I can see why it's attractive from an operational and from an economic point of view to not have a dedicated team that is responsible for building and maintaining an observability pipeline and making sure that it's always up and fixing it when it breaks and those sorts of things. Sometimes it's just more economically efficient to outsource things. So yeah, it depends upon your budget. It depends upon how mature your DevOps processes are and your appetite for maintaining a team looking after tier 1 infrastructure like that. I guess it wouldn't be an architecture conference if I didn't manage to get at least one "it depends" in, right?
And which approach for metrics collection do you prefer, pull or push?
Personally, I like the way that we do it in OpenTelemetry. I like to be able to push data out of my applications and then do something else with it. There's a bunch of different reasons for that. Partly, I think, because it sort of decouples things. So it actually separates out developer concerns from operational concerns. And I know that we're all one big happy DevOps family these days, but there is still that divide between people who think about development and now have a better understanding of operations, and those folks who consider themselves primarily operations people that now have a slightly better understanding of the code that's running inside their containers. So that decoupling, I think, is helpful. It also means that the more operationally minded or infrastructure-minded folks can make decisions without notifying, without really having to involve the developers too much. If I push all of my metrics out to an OTel collector, and that's configured to stand up a Prometheus endpoint, well, I've got Prometheus backend, which is coming in and scraping that. Okay, well, I replace Prometheus with Timescale. Timescale has a push model. So, okay, well, I shut down the Prometheus endpoint, and now I can just push directly into Timescale from my collector. And that's one of the things I didn't have enough time to talk about, was that level of decoupling which the collector produces is another of the really good architectural things that I like about OpenTelemetry. So you have your concerns, you have a piece of code, there's a local collector, and it's configured to do some stuff. But that's a downstream concern from developers.
Okay, and last question. So data sampling usually misses the samples of the real production incidents. OpenTelemetry have introduced some dynamic data sampling collector configurations. Can you share any real-world experience with them? How well do they work compared to other enterprise tracing solutions?
Okay, so this was basically a question about OpenTelemetry and how it compares to other enterprise scale. Okay, so first of all, the bad news. The chances of being able to get a vendor-supported, completely proprietary tracing solution, those days are numbered. The number of people who are retiring their tracing components and replacing them with OpenTelemetry is only growing. So fairly soon, you may not have much of a choice. So you should think carefully on that point. Secondly, the introduction of tracing can be a little bit sensitive, partly because people don't always think about things like the sampling rate. I saw one instance where just a fairly normal set of microservices, which didn't really need it, turned on 100% sampling. Now, that's going to have an impact. With any kind of monitoring system, there is a trade-off. The collection and the analysis of data uses computation. The more data you're collecting, it's like quantum mechanics. The more you're disturbing the system. So without having thought about things like data sampling rates and doing some experiments as to how much data is actually going to flow at various rates, you probably shouldn't switch it on in production. Having said that, once you get used to it, it really isn't as scary as a lot of developers seem to think. So I would say, another anecdote I can share is, in the most recent round of performance testing of the OpenTelemetry libraries that I've done, and again, this is a Java number, it's taken us about 4 weeks to find a space in the performance arena, if you like, where we can detect the overhead of OpenTelemetry libraries at all. The first 3 weeks, we found bugs in our stack the performance bugs in our stack before we could actually even detect the libraries being switched on or not. So once you get it right, it should be very low overhead. I mean, I'm talking low single digits of percent, 1 or 2%, down at the level of the noise. And of course, that's with sampling, so you're probably only taking 1% of the successful traces. So it can be done. And I would say, don't be afraid, carve out some time, play with an instance in staging, and see where you get to.
Thank you, Ben.